So this video is going to be on the expanded octet rule, Lewis diagrams, and formal charges. So some elements obey the octet rule, which you would have learned about in GCSE, where they want to have 8 electrons in the outermost shell, but lots of elements don't, like hydrogen, helium, only need 2. Beryllium, boron, aluminum, lots of period 2 elements don't need the full amount, and period 3 elements actually can have more electrons than the octet rule. They can, because of their d block, they can fit extra electrons into the d block orbitals. So here you can see some different examples of different molecules that have 8 electrons around the central atom and the shapes that they form. And here are some examples of some different molecules that have the central atom that has more than 8. So breaking the octet rule, you can see around all of these ones, you've actually got 10 electrons, so 5 electron domains. And around all of these ones, you've got 12 electrons, so 6 electron domains. And you can see the names of the shapes. So if you have 5 electron domains, then you have, it's all based, the electron domain geometry is this trigonal biopyramidal shape. Looks like this. And as you start to replace the bonding pairs with lone pairs, we start to have different shapes forming, such as seesaw, T-shaped, and linear. So have a pause now and try to identify the names of these shapes. These all have 5 electron domains, so what are their names? Also a good idea to practice drawing them. In the exam, the mark scheme, you can see how you get these wedges and these dashed lines there to show 3 dimensions on a 2D sort of surface. The filled in wedges, obviously coming out of the screen, and the dash going into it. If you don't do them and you just do lines, that's fine for IB spec. You'll still get 4 marks in this case, unless the question asks you to use wedges and dashes, which in the previous spec I've never seen a question do that. So here are the answers. Here are some ones with 6 electron domains. So again, let's try to match the shapes. There's the names of the shapes. Good idea to sort of cover them up, practice drawing them. Again, don't worry too much about the wedges and the dashes, as long as you can get the right, roughly the right number. Well, it's about getting the right number of bonding elements and lone pairs around the central atom. And obviously the bond angles and shapes you need to memorize. Okay, here's the answers to those, the shapes. Here's some questions to try from the textbook. So pause the video, have a go at these questions. And these here, so again, pause the video, have a go at these. Here are the answers from the textbook. They're generally all pretty straightforward. We'll just go through how to do 1 or 2. Let's do B. Okay, so step 1, you want to work out its Lewis structure. So you can see put the central atom in the center and then connect it to the other atoms. If you're struggling to figure out which one's the central atom, obviously it's the one which is, there's one of them. If there's more than one, which is just one, it's going to be one to the furthest to the left on the periodic table, generally. Okay, so there's our start of our Lewis structure. Calculate how many electrons there are in the valence shell of each atom. So we've got 7 for chlorine, group 7, and then 6 times 3. So you've got 6 times 3 is 18, plus 7, 25. And then you've got a negative charge that adds out as 1, so that's 26 electrons. You can see I've already drawn 3 lines. Each of those lines is a covalent bond consisting of 2 electrons, so that's 6 electrons there, so that's minus 6, so 20 electrons to put on. Just put them on randomly, and not obeying the octet rule, where possible. So let's put them on. So if I put on 6 around each oxygen, that will be 18. So that leaves 2 left, which I'll put on the chlorine. And then you ask yourself, is everyone happy? Are they all got their sort of octet rule satisfied? And we can see that everyone does, so that must be its structure. So then we look at the central atom and we ask ourselves how many electron domains are there. So there's 4 electron domains, 3 bonding pairs, 1 lone pair. So that's going to be a tetrahedral structure shape for the electron domain geometry. And then for the molecular geometry, 3 bonding pairs, 1 lone pair. You just need to memorize what that is. So 3 bonding pair, 1 lone pair is triangular pyramidal. And then again, you need to memorize the bond angles. So tetrahedral is 109.5 and triangular pyramidal is less than 109.5. I think it's around 107 roughly, but it depends on the molecule. Oh, I forgot one thing. This is not a correct Lewis structure because I didn't put the charge. So we've predicted the geometries, tetrahedral and triangular pyramidal, and the bond angles less than 100 and less than 107. Sorry, no, less than 109.5 or 107 roughly. Okay, let's do another one. Let's try one which has an expanded octet, which will be that one there. Yeah, one of those. Let's just get rid of this. Let's do F because it's my favorite shape. Yeah, so F, here we go. I saw IF4. So starting off, obviously the central element is I because there's one of it, but 4 fluorines going around it. Whatever, spread out around it. The Lewis structure, the shape, is not important. We're not trying to get the bond angles. We're trying to use this to figure out the bond angles. We can then redraw it with the correct shape if we were asked to, which we're not in this one here. Okay, so we've drawn the basic structure. Let's put the square brackets on now so I don't forget. And the charge plus. Now we need to work out the valence electrons. So having a look, all of these are in group 7. So we're going to have group 17, 7 electrons each. So 7 times 5 is, oh my god, maths, 28, 35. Okay, 1 plus charge, 34. So the plus charge means we take 1 off. So 34 valence electrons. We've already shown 4 bonds. Each bond is 2 electrons, so that's minus 8. So we got 26 electrons to put on. Let's put them all around the fluorines first. So that's going to be adding on 6 to each fluorine. So that's going to be 24. Excuse my drawings because I'm trying to do it with a mouse. Okay, so that's 20. So we've got 1 left over. So 2 left over. That's 24. So that's 26 electrons put on. We can see how iodine is breaking the octet rule. It's got 10 electrons around it. It's perfectly fine. It's huge. It's got D subshells which can put those electrons in. And yeah, let's work out the geometries. So again, this is memorization from the table. You just need to memorize the fact that first we need to work out how many electron domains are around the iodine. So you can see there's 5. There's 1 lone pair, 4 bonding pairs. That's 5 electron domains. 5 electron domains gives us the electron geometry of trigonal bipyramidal. So trigonal bipyramidal or triangular bipyramidal, same thing. Bond angle for triangular bipyramidal, again, you have to memorize that. It's 2 bond angles. So look back on the previous table from the book if you can't remember, but try and memorize the bond angles. Bond angles are 90 and 120. But because its molecular geometry has 1 lone pair, those are going to be less than 90 and less than 120. Its molecular geometry has 4 bonding pairs, 1 lone pair. So again, memorization, that is the seesaw shape, which is my favorite shape. So it's got another name, I can't remember, but it's seesaw. So we're going to move now on to formal charge. Formal charge is a really useful tool to identify if you have different possible Lewis structures, which is likely to be the correct one. It is not foolproof. It is just a way of giving you an idea of what possibilities could be more likely. It doesn't actually take into account everything. So on this slide, we can see we have 2 possible structures for carbon dioxide. Lewis structures, the Lewis formulas tells us that both are possible. But which one is correct? Oops. So formal charge allows us to work out which one's more likely. So to work out formal charge, we use the following formula, which you're not given in the data book. You need to memorize this formula. So formal charge equals V minus B plus L. V is the number of valence electrons in the unbonded atom. B is the number of bonding pairs. So it's not the number of electrons in the bonding pairs, it's the number of bonding pairs. And L is the number of non-bonding electrons. Let's look at an example. Let's work out formal charge for this one here. Okay, so we've got we're looking at the formal charge. So step one, let's look at the chlorines. So the chlorines formal charge is going to be equal to their valence electrons. So valence electrons for chlorine is 7 minus number of bonding pairs, which is 1, minus the number of lone pair electrons, number of electrons around lone electrons, which is 6. So that's going to give us a formal charge of 0. Let's do it for nitrogen. So formal charge, nitrogen's valence electron is 5. It's just from the periodic table. You can see it's got 3 bonds to it, so it's going to have 3 bonding pairs. Notice I don't put 6 there. It's sort of using 6 electrons to fill its outer shell, but we just count 3. And then it's got plus 2 from the lone pair. So again, it equals 0. Okay, so we got a formal charge of 0, 0, 0. These are all equivalent, the chlorines. Now, if formal charges all come out as 0, that's good. That means this structure is likely. The closer to 0 they all are, the more likely the structure that this is the correct Lewis structure. So here's all that working a bit more neater from cognitive. Pause the video, have a look. Just what the working we were just doing then. Okay, let's go back to this carbon dioxide. So you've got 2 structures, structure A and structure B. Okay, so you can work out the formal charge of them. So have a go now, pause the video, work out the formal charge of the carbon and the oxygen in both structures. Okay, so for structure A, you should have got a formal charge on the carbon as 0. You can see the working formal charge equals its valency, which is 4, group 4, minus the number of bonding pairs, which is 4, plus any lone pair of electrons, which is 0, equals 0. So carbon 0, oxygen 0. Whereas structure B, we get a formal charge of oxygen on the left as being +1 and oxygen on the right as -1. So structure A, all the formal charges are 0, so therefore structure A is more likely. Pause the video and try this one. Work out the formal charges of both A and B, of each of the atoms in it. You can see the F's are all equivalent in A, but not equivalent in B. So when you work out the formal charge, you see again A, got formal charges of 0, 0, whereas in B, you've got formal charges of -1 on the boron. My face is covering that, but whatever, and the fluorine bottom right. Basically, this one's got 0s, this one hasn't got 0s, structure A is more likely. Again, pause the video, try this one. Okay, so you can see, again, this side, we got structure B, that's got 0, 0, 0, 0s, more likely. And the structure on the right, on the left, has got non-zeros, so less likely. Yeah, this example here, so we can see how, oh yeah, I mean structure B is just definitely more likely because it's all got 0s again. So we get the formal charges generally because of coordination bonds. So coordination bonds are where you have one atom giving both electrons in the covalent bond. In this example here, we have oxygen giving both its electrons to a hydrogen ion. The donor atom that's given away generally have a formal charge of +1. The formal charges will add up to the total charge of the ion or molecule. So you can see there's a charge of +1, so the formal charges will add up to +1. We work out the formal charges. We can see that oxygen comes out as +1 and the hydrogens will come out as 0. Get another example of an ion. So you can see the ion has a charge of -1, so the formal charges should have come out to add up to a total of -1. And they do. You get all the chlorine 0 and iodine is -1. Okay, again, let's work out the formal charges. They will come out to -2. So we get situation A and situation B. So you can see both of them have a situation where you've got, there's not one situation where everything is 0. So which one's more likely? Well, you want to choose the one that has the least number of atoms having a formal charge. So you can see in structure A, you've got the sulfur's got +2 and all of the oxygens are -1, whereas in structure B, the sulfur's 0, most of the oxygens are 0, and 2 of the oxygens are -1, so the structure B will be more likely. Mentioned before that formal charge doesn't explain, it just gives you which one's more likely. It doesn't tell you definitely, and its main limitation is the fact that it doesn't consider electronegativity, so it doesn't take that into account. So obviously the atom which is more electronegative is going to be pulling electrons closer towards it, and it doesn't, formal charge doesn't work that out. So for example, here we've got two structures A and B, and you can get two valid Lewis structures that is formed. You can see that both have the same formal charge on atoms and the same net charge, which would suggest equal stability. However, structure A is actually observed because we actually need to consider electronegativity as well. Okay, pause the video, have a go at these questions. And here are the answers.